A 180 hertz wave and a 200 hertz wave combine through superposition to make the wave shown in blue at the bottom. What is the beat frequency of the combination of waves? I'm going to show how the wave at the bottom was generated. It can be found by adding two waves together. Let's say I call the top wave Y1 and the bottom wave is Y2. Then the resultant wave is found by superposition by adding wave 1 plus wave 2. We can give formulas to these waves. The generic form of a sound wave could be a periodic function times omega, which is the angular frequency, times a variable t, which is time. And so what I'm going to do is I'm going to make a formula for the top wave. I'll also come up with a formula for the bottom wave, and I'll show how when we add the two together, we get this result below. Okay, now there's a formula for omega, the angular frequency. It can be 2 pi times f, which is the frequency of the wave. So I'm going to apply that here to the top wave. We know the frequency of one of the waves is 180 hertz, and the other wave has a frequency of 200 hertz. If I look at the crests of the waves, it looks like the top wave is actually the higher frequency wave. The reason I'm saying that is we see here that the peaks are pretty much lined up vertically. But as we go forward, we see that the top wave completes its cycles just a little bit faster than the bottom wave does. So that leads me to state that the top wave must be the higher frequency wave, and the bottom wave must be the lower frequency wave. So with that in mind, the formula for the top wave must be sine of 2 pi times 200 hertz, and then the bottom wave must be the sine of 2 pi times 180 hertz. So what I'm going to do in Desmos here is I'm going to add these two waves together, and let's see the picture that we get. I'll define y1 as the sine of 2 pi times 200 t. We're going to zoom in a bit here. I'll change the time axis so that I can see the wave a little bit more clearly. Now let's type in a second wave, y2. When the waves are overlaid over each other, we can see that there's a stretch where they're in sync practically, and then there's a stretch of time where they're out of sync. And so what's going to happen is at the times that the waves are in sync, they're going to add together constructively when we do y1 plus y2, and then this peak is going to get pretty much twice as tall. In this region here, though, we've got a crest matched up with a trough, and so when we add those two wave parts together, they should cancel out to 0. Let's look at the resultant wave when we add y1 plus y2. So the green represents the sum of the two waves, and if we hide the old waves, we can see the pattern that is created. And we see constructive interference at times when the original waves were in phase. So that would be here. And we see destructive interference when the waves were 180 degrees out of phase. That would be here. Let's hear these sounds together using a tone generator. I'm going to set one of the waves to 180 hertz. Then I'm going to create another copy of this, and we'll set this one to 200 hertz. Let's hear the waves together. So the vibration you hear is due to the beat frequency, it's called. If we were to raise the 180 to be in a little closer to the 200, you hear a little bit different beat frequency. And if we go even higher, the beat frequency slows down. Let's see what is causing those beats that we hear. If I raise the frequency of the Y2 to 185, we can see a longer length of this constructive region. If I raise it to 190, we get an even longer length. And then 195 looks like this. 199 would be an extremely long time between beats. So let's match those up with what we hear. Here's the sound for 180 and 200 together. When there's only 1 hertz difference between the waves, we can really hear the times of constructive interference and destructive interference clearly. So there is a formula for what we call beat frequency. The formula for it is FB equals F1 minus F2, where FB is the frequency of the beats that you hear. The beats would be the constructive interference points, such as here and here. So they call this a beat, and this is a beat. F1 is the frequency of the first wave, and F2 is a frequency of a second wave. So to calculate the frequency of the beats in this particular question, I'm going to do 200 hertz minus 180 hertz, and use absolute value just to make the frequency of the beats a positive number. The frequency is 20 hertz. If we go to the graph, we should be able to identify the period between the beats. It looks like 1 point of constructive interference is 0, 0. The next constructive interference happens at 0.05. So the time between these would be the period of the beats. 0.05 seconds. So the period between the beats is 0.05 seconds. And therefore the frequency of the beats should be 1 over the period of them, which is 1 over 0.05, and that is 20 hertz.